Okay, I just want to thank everyone for attending the Planetary Science Seminar Series again, by the uh, sponsored by Survey, CASA Moon node within Survey, and the Institute of Meteoritics. And it's my pleasure to introduce today's speaker, a really good friend and colleague, Justin Simon from the Johnson Space Center. And he is going to speak upon the generation of felsic rocks on the moon and their role for lunar volatiles. Justin, go ahead, take it away.
Well, thanks for giving me the opportunity to speak to you all. I'm going to talk about felsic rocks on the moon and their role for lunar volatiles. I bit off probably too much, and so I come from a terrestrial background, and I studied a lot of felsic rocks on Earth, and so sort of half petrologist, half geochemist, half isotope chronologist. And so I'm hoping to provide a sort of a high level introduction to these, both the generation of felsic rocks and their role for lunar volatiles. But just taking a step back, and I won't get into this in too much detail, but understanding the volatile budget of the moon is important more generally for understanding the distribution of volatiles in our solar system, but in particular the early solar system and how this distribution changed as the solar system evolved. This is not just because volatiles are essential for life and other near surface processes, but it's also important for how they affect physicochemical processes, particularly in magmas, how they are generated, how they degas, and they can have significant effects both in terms of local and sort of planetary scale differentiation. So I'm going to move along. If there are questions, I probably can't see the chat, but if someone could just jump in and let me know, I'm happy to clarify. So why study lunar silicic or felsic samples and silicic surface features? This image on the right is showing some relatively recent remote sensing data or images that have been followed up with spectroscopy that show that there are silicic features on the moon that are probably more abundant than previously recognized. Certainly, when I started studying the moon, the felsic samples were the rarity, and there weren't really any connection to features that we were trying to see on the moon. Like I mentioned, this is a talk about not just the felsic magmas, but also volatiles on Earth, and I'll get to this theme a couple of times. The formation of felsic rocks can concentrate volatiles on other rare materials, and therefore, for our sort of 11th floor look, these types of rocks may represent a vital in situ resource for future missions. And then finally, their petrogenetic origins are important for understanding the sort of secondary crust formation and, of course, the volatile evolution of the moon. Oops. Okay, so I again, and I apologize if I come across a little pedantic because for some of you, but I wanted to make sure that I was reaching everybody. I put together this cartoon, which I'm calling the anatomy of a terrestrial silicic magma system. It's really if you want to think about it as the plumbing system. And there are a couple of points that I want to make here. And the first is that at least on Earth, these systems are underpinned by massive amounts of mafic mantle-derived material. And so it scales in an exponential way. The other thing I wanted to point out, so the point being is if you're going to have volcanism, silicic volcanism, you need to have a ton of mafic volcanism, or excuse me, magmatism beneath it that's generating it. And it's generated by a number of different processes. But basically, if you think of it as a filter through the crust, it's starting out as a basaltic composition, and then through a variety of different processes can become more silica rich, we call that andesitic, and eventually rhyolitic or felsic before it erupts or is placed on the surface or exposed on the surface. The other thing I just wanted to mention is that we have a number of different terms for felsic, silicic, what have you. And I think of things in geochemical terms. And so silicic is sort of the term I use, or rhyolitic. But there are plutonic or intrusive varieties, granites, and then there are volcanic varieties or extrusive varieties. But again, the main point that I'm trying to make here is that there's a massive machinery below the surface that is required to produce these silica-rich rocks. And this same process, at least on Earth, concentrates alkalis, volatiles, all other incompatible components that don't go into mafic or mantle minerals and that are therefore concentrated. So another way of looking at the composition of planetary materials is in some type of major element diagram. And this is the total alkali versus silica diagram. And the point I wanted to make here primarily, so the silica versus the sodium and potassium, in showing the various different rock types, these are igneous rock types, is that we live on a basaltic planet. Mars is a basaltic planet. The moon is a basaltic planet. The highlands are still basaltic. These are all mafic rocks in general. At least on the moon, we don't have evidence for andesites, the intermediate composition, at least not direct evidence. And then also on the moon, we have these rare extreme compositions, these more evolved felsites, showing some pictures on the right of some beautiful examples on Earth. Obsidian Dome in California, near the Long Valley where the Bishop Tuff erupted from, and then some of the granites that are in Joshua Tree in Southern California. I'm originally from California. Again, on Earth, these silicic or felsic rocks are high in alkalis, water, and other constituents that are incompatible in the mantle and mafic minerals. So because we sort of have two themes going on here and lots of samples, I wanted to just sort of present a couple takeaway points. So this is when your ears perk up and you sort of take in, this is what I want to get across today. The moon has silicic lunar features. Excuse me, the moon has silicic features. All of them are lunar. However, their formation processes remain unclear. And I haven't talked about this yet, but there is an apparent age discrepancy between the ages derived from samples and those derived from the silicic surface features. This is something I think is underappreciated. And then based on the samples that my group has worked on and others as well, but primarily I'm going to talk about the ones my group has worked on. Felsic rocks do record significant water, but others that perhaps are more texturally pristine don't. And so this body of work, I think, adds to a general working hypothesis. I wouldn't claim it completely being my own at all, but that I feel like is a hypothesis that's in progress. We're testing this, but that is basically that the moon didn't accrete with Earth-like water abundances, and if it did, it was largely degassed early on. And I know others have made that point as well. There are reservoirs that are enriched in volatiles, and these must reflect local concentration or late addition. And I'm going to focus a little bit on those two themes in this talk. Okay, so this is I'm backing up again here. There are some locations of the silicic volcanic features. These are LRO diviner data. It's really the squares. These are in the Porcelarum Creek terrain outlined by the dashed line. And these are also called the red spots. And I won't go into this, but they're looking at spectra, UV relative and visible, to define this. And there's a large body of work, probably maybe some of the authors are online. But this is super exciting because this is, like I said, these remote sensing observations are relatively new. We didn't have these when I was in grad school, or at least I wasn't aware of them even being a thing. And then again, here's a close-up of one of those centers. This is the Compton-Belovich volcanic complex. And the point here is not go into the details, but just to say that this feature does exhibit features that are common to terrestrial silicic magma systems. It looks like there are landforms that could be domes or flows, and maybe even a caldera. Likewise, there is evidence for water, or at least hydroxyl, that is been recorded in the same location. So this talk is really about samples, and so I'm really trying to understand whether and how we can link the sort of the detailed records that we have in the samples to these types of landforms. And so, most of the sample people in the room have a picture like this of them poring over rare Apollo samples in the Apollo Clean Lab here at JSC. And again, these felsic samples are pretty rare in terms of volume, in terms of mass, et cetera, but mighty. So, we work in saw kerf, rejected fragments, all these various different breccias. Some of them are pristine, and many of them are not, but we have been poring over these over the years. So I wanted to start, and again, I'm going to be going over some things fairly quickly, and I'll just keep things at a high level, but I wanted to talk about this comparison between the samples and the surfaces, and I was going to then therefore talk about radioisotopic sample ages and compare them to crater counting surface ages, and I won't be able to get into the details at all. I'm showing a picture of our TIMS machine here at JSC on the right, and then just listing some of the common radioisotopic chronometers, lead, zircon, samarium, neodymium, argon. These are all very classic and very powerful. We also use at JSC a less common chronometer, the potassium-calcium system. And this one is similar to the samarium neodymium system, except that it's involving major elements. And I'm going to talk a little bit about how that difference provides an advantage and allows us to probe the major element or through rock defining composition of where that sample came from. So it's a way of peering back to its source. So that's coming up. So some samples have, as Lars Borg talked about previously a couple of weeks ago, different ages or disturbed ages, indicating complicated history, and some don't. So this is an example of one of the samples that we've worked on. We've provided some of the ages, but many other people have looked at the age. And so you can see, relatively speaking, this is a well-constrained formation. This is a piece of granitic material or felsite that's in the 14321 breccia. And this is a rare sample, and the fact that we get multiple ages and multiple labs matching is also rare. This is a different sample, 14303 breccia, and it contains evidence for a more complicated history. You can see some of the very tightly constrained zircon ages, and then some of the more disturbed ages. And I will not get into this in too much detail, but these different systems, as Lars was getting at a couple of weeks ago, are powerful in combination because they actually have different chemical behavior in some cases. And so some of this disturbance can then be understood as sort of the geologic history. I won't go into the crater counting of surface ages, but basically, I think most folks understand that as a surface ages and is impacted, it retains craters. And so at 0th order, more and larger craters on the surface indicates a larger age. There's math behind this, and there's a lot of hard work and thought thinking about how those ages are retained. But essentially, they come up with a frequency, a cumulative crater frequency versus size plot, as shown here. These are just examples of some of the silicic centers that we were, or I was just alluding to. And then they like an isochron, can define an isochronous slope, if you will. And you can see some of the ages that are being compared to the data here by Wagner et al. And so this is sort of like the summary of the age part of this talk. Basically, if you take the crater counting age at I don't want to say at face value, but based on the experts, and you plot those ranges and their uncertainties, you get ages that are generally younger than 4 billion years. And I was somewhat surprised by this because when you look at the samples, although there's some spread and there aren't that many in either of these two data sets, but there's a clear dichotomy between the samples, which appear to be quite a bit older than the surface ages that you see for the silicic features that are being studied remotely. Okay, so let's talk more about the samples, and this is going to transition into volatiles very shortly. This sample, the 14321, 1027 is a very famous sample. I had the opportunity to work on it several times. And we're gonna talk about this sample in a couple times. It's an ideal situation because it has such a nice chronology or concordant age record. And you'll see I talk about this as the best granite. Roy Christofferson makes fun of me because I talk about it as the best granite on the planet a lot. So this is the potassium calcium isochron, and the reason I'm bringing this up is that it's not just an age, right? So it does have the same type of topology, if you will, an isochron diagram. It's got a slope that you can assign an age and uncertainty to it. This is a 95% confidence interval, but it also has an intercept that is, you can run it to the right, or excuse me, to the left here. And this intercept can then be used to model how much radiogenic ingrowth must have happened at the time of formation, since the time of formation. And so what does that look like? This is a somewhat complicated diagram, but what I want to get across is that on the bottom is age, and these are evolution curves. And on the vertical axis, these are the isotopic ratios of 40, which is partly the decay product of potassium 40. And that intercept, which is the blue circle with uncertainty of this granitic material, plots because of the isochron age and because of its intercept value right where it is. But those evolution curves, those numbers, 0.3, 0.5, 0.7, 0.9, et cetera, those are the potassium calcium, that's the potassium calcium ratio of its source. And so that's basaltic, that's andesitic, and that's rhyolitic. And just getting back to, so this is significant. This is telling us that, this rock had a source that was maybe andesitic or possibly rhyolitic or granitic, which is, something that we couldn't have gotten from just the samarium neodymium or zircon, or, lead zircon age, et cetera. So that's a pretty interesting observation. I will note that the situation only gets more evolved if you don't use the initial age of the Earth, of the Moon, to calculate these model curves, but the 4.3 billion year lunar magma ocean timing that Lars was talking about last week or 2 weeks ago. Okay, so now getting to the volatile part. So there are a number of studies, and they're growing quickly, looking at lunar materials. And historically, lunar materials were thought to be bone dry, although bones are not that dry. But the point being is very, very deprived of volatiles, including water or OH. We now know that some have, well, all probably have some evidence of volatiles, and some actually indicate very wet, nearly terrestrial mantle like compositions. And so really the question is, was the early moon as wet as Earth? What is going on? And so the approach really is looking at the samples, especially ancient materials, in a variety of different mineral systems. And I'm probably gonna not have time. Well, I definitely won't have time to go over all the data, but I probably won't have enough time to give some of the other systems that I haven't been employing credit. But I do want to get to that in a second. But before I do that, what I wanted to mention was just, this is a nice cartoon from Jess Barnes in one of her papers talking about the same problem, right? Like how does the moon get its volatiles? We know that there are lunar volatiles now. Were they there from the beginning and then lost? Were they delivered slightly later or much later? And again, these are our cartoons, and we don't want to over interpret them, but that's the idea is, we have volatiles. How are they originating, and how are they being redistributed, and how are they evolving through the differentiation of the planetesimal? And so this gets back to the lunar magma ocean model. This is a fundamental model for how we understand the moon formed. This is not new to, I don't think, anybody in this audience, but it's also, without getting into the petrology of this or the petrogenesis of how the moon differentiates in detail. I just wanted to talk about in general how this kind of model has implications for how volatiles are redistributed in the lunar materials. And so as you go from left to right, there's time. This is a nice cartoon from Jennifer Rapp when she was a postdoc at LPI. And basically showing, you're starting to you have a quenched crust, but primarily you're a molten body, and then you begin to crystallize these mafic minerals, and the incompatible elements, including volatiles, are being concentrated through time as you move to the right. Eventually you start forming plagioclase after like 80% crystallization. Those actually float. It's a pretty dense melt. And you get this sort of sandwich situation where you potentially concentrate all of the incompatible elements, but at least concentrate some of the incompatible elements into this creep zone. And this is a model, but it's a useful model. So again, this is where the incompatible bits are in the moon, at least according to this model. And this is where I get into the fact that I'm not going to talk about many of the previous other approaches to addressing the volatile record of the moon, but just wanted to mention that they exist. There's some exciting melt inclusion work. There's a lot of apatite work, and you can see that there are very disparate answers here, and some of that is geologic. I would say probably most of it is geologic. An apatite is a late forming phase, and in some cases may not be forming from a melt. And so depending on the question that you're asking, it may dictate what the record it contains is. Likewise, there are other stoichiometric constraints to a complicated mineral like apatite. So our approach is one where we use an ion probe, the nanosims in this case, to look at the potential, I'm putting in quotes, creepy water in feldspar. So this is a nominally anhydrous mineral. And so we're trying to answer the basic question is, do alkali feldspar from granitoids that are presumably derived from these creep-rich sources, do they have measurable water? And I'm showing in my ugly overlay of red felsic magma bodies coming out of that creep layer there on the right. And if so, do these felsic magmas, do they remove water from the interior during the secondary crust formation? And if they don't have water, then what? And then the spoiler is that the felsic samples that we've worked on, we find both very wet and very not wet or dry values. Okay, so this is basically where we're at. We want to look at a diversity of rocks with felsic lithologies. I'll be talking about multiple clasts from 3 different breccias in this talk. I will also just have a shout out to additional follow-up work through the ANCSA program, in which we've identified some other felsic fragments that we're doing similar and extended work. And then I'm involved with a group led by Timmons Eckerson, one of the ANCSA 2 proposals that's following up on some of these samples and some others along the same sort of desire to understand how these felsic rocks form. So anyways, you can see on the left, there's a diversity of zircon ages for these felsic rocks. Is there variability in the volatile content related to their chemical composition, their petrologic diversity? What about their age? These types of questions will help us potentially understand the volatile history of these felsic rocks. I would be remiss to not point out that a big part of what made this work that we did stand out is that we coordinated every measurement with detailed microstructural analysis. And we're doing this to look at possible disturbances to understand the context, the petrographic context of our analyses. So we used the focused ion beam TEM approach, and this was work largely done by Roy Christofferson, and that's included in part in the 2020 paper. And so this is the general workflow. We identify a breccia or a lunar sample that has these types of samples in it. Then we work to get allocation of some of those samples. Then we do imagery. Then we do the nanosims or the volatile measurements, and then do the follow-up electron probe work to address the composition of the minerals that we studied. And then we finally do the sort of TEM level microstructure work. I'm not showing the chronology in here. That's a separate line where we basically split the sample into various aliquots. But that's the general bit. And we order it in this way because we don't want to affect the volatile measurements. And we know that the other, especially the electron probe work, could at least locally affect them. Okay, so I'm going to go through, how am I doing in time? I'm doing okay. So I'm going to go through a number of samples, and I will talk through them, and then I will tell you what I think they're telling us. So there are a number of clasts that were contained in the Breccia 15405, these are granitoids that we characterized. And this is work that was led by my former postdoc, Ryan Mills, using an imaging mode. So on the left are electron beam images, and on the right are actually a combination of electron and ion beam images. And so this is, excuse me, I got ahead of myself. This is the picture of the ion beam images of that same sample. You can see there and there. And so what we found was looking at the regions that were feldspar and SiO2, which were intergrown in this granitic class or felsite class, we found considerable amounts of water. This is, again, these are nominally anhydrous minerals, but the feldspar had 20-ish ppm water, and the quartz had, or the silica had much less, but still some. And so this then gets into some of the technical details, but you can then predict what the melt composition, the volatile composition of the melt from which these phases flew from, based on how that water or that OH is partitioning between the melt and the solids, and there are assumptions in there. But basically, if you use the range of assumptions, these are super wet. What I mean by that is that, like, this is half or 1.7 weight% water, and these are by far the wettest lunar magma that's ever been reported. This is wet or wetter than most granites on Earth. So this was a significant discovery. There's a catch, but this was a significant discovery. So that was the sort of, that was the initial chapter of the JSC, or I should say my group's volatile story of felsites. Feldspars from the moon have measurable water. Feldspar is common and should provide an independent estimate of magmatic water contents for a range of different lunar and other extraterrestrial materials. And the class that we studied indicated wet magmas. They're old and they're likely disturbed. And so what we wanted to do, as I mentioned before, is look at younger, perhaps more pristine samples. And so that's sort of this next and final chapter of this talk. So again, using an ion probe, rather than doing imaging, we did spot analyses. I won't get into the details here, but essentially, we're using a similar or an identical instrument, actually, but using it in a different mode. Both have benefits. And this work was done at Carnegie, I guess now 6 years ago. And so I'm going to go through a number of samples that I didn't show, but that we talked about before. These are all felsic clasts, fragments. It's always unclear whether the modal abundances or assemblage of the phases that are in this relatively small class are representative of the rock. So there are lots of assumptions, but you can see we have alkali feldspar that's intergrown with silica. We have pyroxene. We have plage. The types of phases that are consistent with these types of rocks. And so I'm just going to go through a series of these sort of overlays showing different clasts and showing the measured volatile content. So in this case, this plage has 6 to 8 ppm water based on an average of, well, that's not an average, sorry, that's a range of 3 measurements. So there are other samples that we ran into. Some of them were not felsic. They were white, but they were not actual felsic. And so this is an example of that. This is a creepy basaltic class that was in that same breccia. It did have potassium feldspar, but it's not a felsite. And so again, we measured when we could, we measured the feldspar, and we saw that it had relatively low concentrations of water, if you will. And then another final, I guess maybe there was one more that I deleted. Here is is that best granite on the planet. This is a feldspar that was extracted from the work that we did to do the chronology, and mounted in indium and polished. And you can see that this has a quite low value, about 2 ppm. This is the leftovers from some of the samples. Again, another white class that I was hoping was going to be a felsite, but it turned out to be not. But we still measured its plagioclase so that we could have some point of reference. And so this is sort of a diagram showing, these are all hard measurements, but this is a diagram showing sort of a summary of that. And the geologic time on the x-axis is not well calibrated, but there's a general sense from left to right based on the radioisotopic ages. Some of these have greater uncertainty than others, but they are placed in approximate order. The volatile abundances are quite precise, and they are obviously mostly low, with the one exception of the work by Ryan. And then the other thing to mention is the black symbols are feldspars that are contained in mafic rocks, and then the red symbols are feldspars that are contained in felsic rocks. So I didn't mention this slide came from a previous talk where I talked about some previous data, but these data have been recalibrated because there was a recalibration in the comparison between 2 different techniques, the FTIR technique and the ion probe technique. And so those values dropped to lower values. All the ones on the right are using the same calibration as the ones on the left. Obviously, this is this crazy high wet rock that we discovered in 2017. And we expected maybe that we would see a positive correlation between the alkalis and the water, so that this rock may indicate that. But then when you look at these other 2 rocks, you wonder, oh, what's going on with those 2 lower rocks? I think the next slide is where I answer that. And I'm just going to skip that slide so I can make the point. But what you see here is actually this relationship between water and the potassium-calcium ratio, and you see the opposite of what we expect. This granite that I've called the best granite is really super dry, more like all the mafic samples that we characterized. So why is that? Okay, so in this last, I guess, 15 minutes, I will discuss some of the microstructures that we see in here, and then we'll open it up to some questions. But the microstructures are really key to us understanding what these records of volatiles mean. So this is the first sample, the one that Ryan worked on that was very wet. And what I'm showing here is a series of images, partly because I want folks to understand what was done, and partly because there's a story here. So the FIB, the FIB, that is a focused ion beam that is basically a blading away, sputtering away sample around a little piece of, like a little window, if you will, a little foil that is then pulled out of the sample, and that in the middle section there you can see post the fibbing, you can see where it was pulled out. So it crossed the feldspar and the SiO2. And then on the right, what you're seeing is you're looking through the plane of that window. You're looking, rather than looking down, which would be along the top edge, you're looking through the plane of the window, and you can see the minerals, and then you can interrogate those minerals with other beam, primarily electron beam techniques, but others as well, to understand the mineralogy ultimately, but also the mineral chemistry and the mineral structure. And so that's a sort of long story to say that we looked at the feldspar in this rock with the electron, the electron probe before we did the fib work, and we thought the analyses were a little bit were pretty good. They were a little bit, we only made a couple measurements because some of these measurements are some of these phases spots are pretty small, and we had to get some more clasts. But when we went back and did a bunch more, and you can see this in the lower right, this is a compositional space for feldspars. You can see that between the calcium or the plagioclase end member and the alkali feldspar or the orthoclase end member, which the data don't fall along that join, which is the sort of stoichiometric feldspar. So that's the first sort of indication that something is going on with this sample. It is missing volatiles, if you will. The data are closer to the silica and the aluminum. And so, if there's a volatile loss, if there is some evidence of alkali loss, then what does the water measurement of this represent? And so basically we're going through and doing a similar combination of looking at the mineral chemistry and the mineral microstructures for these samples that we just talked about in terms of their volatile content. And so here you can see again a larger in the triangle, the ternary of anorthite, albite, and orthoclase. So that's calcium, sodium, and potassium end members of feldspar. And this is again for this intermediate, this composition that has an intermediate potassium calcium, but it also has ironically an intermediate volatile abundance in the feldspar. And you can see that there is some deviation from the ore or the orthoclase corner that's indicative of less than expected alkalis in that end member mineral. So when Roy took out the fib section and looked at this in detail, and there I have like 10 different versions, different images from these for each of these samples, and I'm only providing representative ones. You can see if you're an expert, if you look at the lower right, you can see indications in this so-called bright field image of some disturbance, and I will show a little bit more of that in a second. But just to emphasize, if you look at the yellow traverse in the middle, on the top middle, you can see it's going across at least two different phases, going from sort of what is believed to be a plage through over what I think is a SiO2 back to a plage composition, and I'll show that next. You can see the window on the upper right. I recognize that these grays are somewhat subtle. But when you look at that window, if you will, and characterize it in detail, looking at the diffraction, looking at the microstructures, you can see that unlike the first sample that we looked at that was basically not crystalline, these minerals are crystalline, but there are defects. And so the sort of the story for this sample is that we look at the minerals, they're crystalline, but there are some defects, and they're being concentrated along boundaries, and this is often indicative of some type of shocked history. And so then finally, looking at this relatively young granite, best granite on the planet, looking at the mineral chemistry, and I won't show much of it because it's kind of boring, but looking at the microstructures, we see that we have what we expect for compositionally for an alkali for an orthoclase, a potassium-rich feldspar. It has a very tight composition, has not lost those alkalis. This on this right here, you can see a comparison of the measurements that we made on a number of thin sections and thick sections of that same granite clast or granitic clast from 14321, which all fall within that red box, as compared to some of the data. We have a ton of data, but there are also some literature data showing how some of these other felsic rocks deviate from that stoichiometrically expected end member. And like I mentioned, I don't have exciting because they're not exciting images of this best granite on the planet. We did pull fib sections, looked at it, and Roy looked at them in detail, and they're wholly crystalline, featureless, indicative of an igneous texture and history. And so this is sort of the summary of those three red felsic rocks with respect to their volatile abundances. There's the 15405, non-crystalline feldspar and tridymite. It's got a ton of water, relatively speaking. Then you have this intermediate sample that has, when I say intermediate, I mean intermediate in volatile OH concentration. It has crystalline mineralogies, but there are shock effects that are present. And then finally, you have this youngest sample from the Breccia 14321, and all of the minerals in there are crystalline and appear to be pristine igneous texture. So there does seem to be two trends. Of course, there are only 3 data points for each trend. But seems to be a direct correlation between volatile content and deformation or impact structures. So that is higher volatiles, more disturbed sample. There also is a broad age shift. Maybe more, the story is stronger to say that these older rocks are more disturbed. But three data points are not better than 2. But we are still in the hunt for more, and we're following up on this work. So now I just finish off with some sort of arm waving, if you will. But basically, our working hypothesis for the moon, not just the felsic rocks, is that the moon accreted with little water or was degassed during its initial formation. It likely was further degassed at the time of the lunar magma ocean. There's evidence that the Urkrete terrain may have also been degassed by impact, but locally some water was concentrated. So the other processes that were more attuned to this talk and that I was focusing on include both the concentration, but also possible addition. And so basically the conclusion that I stand behind still from Ryan's work is that locally there's evidence for potassium-rich Urkrete to have produced rhyolites that likely degassed some regions of the interior. This would explain some of the diversity in the mafic rocks. So there are some, basalt, Maria basalts that are mafic and relatively rich in water, and then there are some that don't. And you need some explanation. So having a degassed sort of secondary crust or later crust would explain that. And then the main conclusion, not unique and is more complementary from the 2020 work, is that locally felsic melts could be produced by the input of volatiles through impactors themselves, the bolides. And so basically, a couple slides for summary. I know I'm running out of time. Feldspar and lunar felsic clasts have measurable water. They provide a complementary estimate for magnetic water when the samples are not disturbed. There is, still reason to think that felsic magmas had volatiles in them, and they could remove them from the interior as they were forming, both in sort of during the primary, but primarily the secondary crust formation periods. But based on a majority of the published work of Faroan rocks, fans and ancient materials, there's little evidence for abundant water, and therefore it either didn't exist or had to been degassed. And then finally, some of the wet felsic materials may reflect some period early on of impact delivery. So I think that's what I have. Looks like I finished right about on time. Thanks.
Great, thank you very much, Justin. Before we entertain questions for Justin, I just want to remind you that there's some more details of Justin's presentation in New Views of the Moon 2 chapter on post-lunar magma ocean magnetism that Justin was a substantial contributor to. And so more information can be reached there. The second thing I just want to announce is that next week we will have Tony Gargano from the LPI, JSC, and UNM. He travels a lot of different places and does research in a lot of different places. And he will be speaking on volatiles associated with the impact processes. So let's go ahead and let's entertain questions for Justin. Anything from UNM?
I see Carl has his hand up.
Yeah, Carl, go ahead.
Hey, Justin, very nice talk. I'm sitting in my studio and not at UNM today, but anyway. But so that was really interesting. I just had a couple questions. Maybe I missed it, but there were no hydrous phases even in that wet granite. And then the second one is, what's the deal with the mix of tridymite and quartz? I mean, when is tridymite stable and when is quartz stable? Is it related to impact heating? Is it some other thing? I was just curious about that because, of course, in a lot of meteorites you see tridymite and not quartz, but here you seem to see a mixture of both. So
Yeah, those are both excellent questions. The first one is, and I tried to be circumspect about this, is there are apatite. I just wasn't talking about them, and I haven't myself measured them in some of these felsic rocks. And that's a really important point because we would love to look at both the non-land hydrous minerals and the apatites from what we think is an actual melt. And we are in the process of doing that. Actually, one of our ONCSA class, we're working on that. We have not gotten all those data yet, so and I don't want to get in front of that work. But they, apatite do exist in some of the felsic rocks, and I did present that one sort of I don't want to say compendium, but the work by Robertson that showed sort of published literature data, and I think that she actually made measurements of some felsic apatite in there, and they were relatively low. But of course, this is complicated by the complications of the site competition that I know you're aware of, that is competition between OH and fluorine and chlorine and what have you. And so depending on the composition of the magma, and I actually deleted this slide, the apatite in those samples, looking if I could bring it up, the apatite in those samples appear to record lower abundances of volatiles, even though the feldspars contain more. And that's a function of the chlorine-fluorine ratio changing with differentiation as you're increasing fluorine over chlorine. So there are these. This is why it's really useful to have this complementary approach where you're looking at multiple mineralogical hydrobarometers, because some of them have compositional control as well. I don't know if that answered your first question or not. Okay, good. And your second question was about the silica polymorphs, and this is something that is also being done. I feel a little, I don't want to get out in front of Timmons's work. He's been doing a ton here at JSC, looking at these materials and looking at the polymorphs. You can make constraints about the thermometry, and we're comparing those to like titanium and quartz, or titanium and SiO2 thermometers. So we have sort of independent things. But that's a story to be revealed in the future, not too distant future. But we're aware of that and we're working on that. I'm sorry, was that another question?
Other questions for Justin? Yeah, Justin, I do have a question for you. Could you just address, I know you started to address it a little bit, but what do you think the relationship is between some of these domes on the surface of the moon and the small, tiny samples that we have in the collection?
Yeah, that's a really important question, and it's a little bit loaded. So in the sample suite, right, we have what I would put them in three categories. We have evolved materials that are sort of discrete clasts, like the best granite on the planet, that I think that we can safely ascribe to an igneous rock. It's a fragment of one, but clearly an igneous, maybe plutonic rock. Then there are some felsites that are kind of messed up because a lot of the rocks are messed up. And they may have been a igneous clast that has been disturbed even beyond those that I was referring to, so much that they're sort of like intermingled into the matrix of the breccia itself. So there's sort of a continuum there. And then in some of the basaltic or mafic rocks, you have little blebs of concentrated evolved melt. Oftentimes you can even see evidence for silica liquid immiscibility in those. I don't think those are representative of a melt. I think those are representative of a late forming trapped component. Not that that isn't interesting or doesn't have a story to tell, but it's definitely not related to any massive igneous body, if that makes any sense. Any igneous felsic body. So getting back to my cartoon, I guess I can flash that up again. This is a a fundamental problem for the moon. Felsic magmas don't just appear. They are based on this huge stack of plumbing. Can you see the cartoon again, Chip?
Yes.
Yeah. And so the point here is that it's difficult to produce a significant dome on the on the surface, even if it's only 10 cubic kilometers of material, if you don't have a sort of a system that is feeding it, right? And in order to collect that volume of melt, it doesn't have to be 100 or 1,000 cubic kilometers of felsic material, but it has to be something. You need to be able to bring those melts together. And if you have tiny distributed pockets of melt in a massive mafic gabbro or what have you, that's not going to work. You can't bring that stuff together. And so it may be an example of an evolved melt locally, but it's not producing the silicic domes on the surface. And we on Earth, again, this is an Earth biased view. Most of us have an Earth biased view. Again, even producing, whether it's partial melting or fractional crystallization or a combination of both, in order to produce kilometers or cubic kilometers of felsic of magma that can erupt to form those surface features, you need to have a major plumbing system like I'm showing in my cartoon. This is there's no scale here by by definition, but you need to have both the heat as well as the mass that is coming in to basically recycle and refine the incompatible elements that can be scrubbed from these mafic rocks.
Great, thanks, Justin. Other questions out there that you would like to ask Justin? If nobody does, I have another question for Justin, but please ask if you have a question. Yeah, another question that I have for you, Justin, is what is the temporal relation? Most of the domes that are on the felsic domes, silicic domes that are on the surface of the moon are commonly associated with on the Earth-facing side, the Procellarum creep terrain area. And clearly they have some relationship, at least on the surface, with basalt flows. What's the temporal relationship between one of these domes or these domes and the adjacent flows of basalt? Do you know, has any relationship been established?
So yeah, that's a really important question, Chip. And I think that the word is still out. My understanding, and I'm not an expert on the crater counting, which is being used to distinguish the difference or the similarity between these ages, is that there's not a clear relationship. It's sometimes even the mafic surfaces nearby are older, right, or younger, or both. They straddle it. So there's not a clear relationship. But it may be that we're looking at it too closely. I mean, certainly the first observation that you made that most of these domes are within the Procellarum creep area probably isn't a coincidence. And like I was saying before, you have to have this major system feeding these these domes from beneath, you know, whether that's like the same type of upwelling hotspot, if you will, in some places on Earth that we attribute it to, for the moon or not, unclear. But certainly that there is sort of a broad concentration of these domes on the near side where we have seen them. It may also be a secondary function where the incompatible elements, including the radiogenic elements, the ones that decay radioactively and produce heat, are concentrated, and that therefore, along with some of the water, those together form sort of the basis for this massive, I don't want to say dichotomy, but like you know, concentration, this regional concentrate, regionally, you know, whatever Lars said before, it was 15% of the moon, this region.
Here's the end of it.
Great, thank you very much, Justin. And if there are no other questions, I just want to thank you again, Justin, for giving this presentation. It was great to hear your perspective on felsic volcanism, silicic and silicic volcanism on the lunar surface. And hopefully you'll tune in for next week's presentation also. But again, I want to thank everybody who joined us, and again, thank the speaker for his contribution. Thanks, everyone. Bye-bye.
Take care.